Okay, go ahead.
Okay. Whoop. Got it. Welcome everybody to this SEMA update session. Or I think Hanley, you're going to do the introduction. Is that right?
Sure, I can do that.
Okay.
So, yes, let's get
Just tell me when
started.
to flip. Just tell me when to flip the slides.
All right, I'll give you a signal. Good morning, good afternoon, and good evening, everyone. So, welcome to this SEMA community update. My name is Hanli Liu. I'm a scientist working at the NCAR High Altitude Observatory, and I'm one of the science co-leads for SEMA. Before we get started with our update, the first stop, Andrew, next slide, is to review the code of conduct. And we want to be respectful, be constructive, open, and appreciative. And the goal is to encourage respectful dialogue that everyone can feel safe to share their thoughts. Our second stop is some important technical points. The meeting will be recorded, and please submit your questions to Slido. And the chat will be disabled and reserved for hosts and support for any technical issues. And we have created a Google form that you can provide feedback after the workshop. And then we have the agenda. Next slide is the agenda. Yes, so we'll spend probably 50 minutes talking about the SEMA background update, project status, applications, and we'll then take a 10-minute break. And when we come back, we'll spend 20 minutes covering all the questions on Slido. And then there will be a 10-minute presentation on next steps. And the last 30 minutes will be plenary discussion. So along with me here are the science co-leads, Mary Barth for chemistry, Andrew Gettleman for climate, Bill Skamrock for weather, and also our software engineer project manager, Jordan Powers is here. We want to thank all the collaborators for their hard work and make this possible today. I think we can get started with our presentation now. Andrew, please take it away.
Okay. Thanks, Hanley. Can you hear me okay?
Yes.
Okay, great. So I'm going to provide an overview of the SEMA project, and then we'll have some launch into some details of anything. Hanley, just interrupt me if my microphone cuts out. I'm using two screens and my AirPods seem to be flipping back and forth, so hopefully it'll stay stable. Okay. So SEMA is the effort to unify NCAR-based community atmospheric modeling across weather, climate, chemistry, and geospace. We've been doing this for a number of years. SEMA has been developed and defined with the community, and the current vision results from a community workshop that many of you may have attended in June of 2020. And there's more information on the SEMA webpage, sema.ucar.edu. There's a lot of information there. I mean, we're going to refer to that, refer people back to that at numerous times during this. So the SEMA vision essentially is it's a configurable system. SEMA is not a single model. It's a way to configure atmospheric models, and it's a way to configure atmospheric models within an Earth system model. That particular framework for an Earth system model is the Community Earth System Model and its associated infrastructure, CESM, that many of you are familiar with. The goal of SEMA is a minimal set of interoperable components. So interoperable components are physical, chemical, upper atmosphere parameterizations, dynamical cores, using common infrastructure and common methods. We're going to talk a lot about traditional components, but this also is designed to extend to things like diagnostics, education and tutorials, et cetera, as we build it out. And the goal is to reduce duplication of effort and bring more eyes and more science applications to the table. So it's really a community working together towards these frontier applications. So in visual form, the current NCAR atmospheric modeling ecosystem looks like something here on the left. We have a series of different models for different scales, ranging from global models, part of CESM, from the atmosphere, chemistry models, the whole atmosphere model, geospace, going down to mesoscale models, WRF and MPAS, specialized applications at higher resolutions of those models, all the way getting down to the large eddy simulation and process model scale. The goal of SEMA is to basically unify all those different functionalities in a common infrastructure and ecosystem so that we can more easily share components across scales and go basically through from process modeling all the way up to global climate simulation with the interactions of all these attendant models and scales in between. So what does this look like practically? So again, SEMA is an atmospheric model. This is sort of the atmospheric model component blown up inside of an Earth system model with a coupler and other component models. Each of these is equally as complex as the atmosphere. I've just blown up the atmosphere, which is I'm calling SEMA. And then in that context, if we just focus on SEMA, there are all these sets of interoperable components and infrastructure. So we have different sorts of physics and chemistry. We have a data simulation component, and we have different dynamical cores. So the following slides show ways to configure this for different applications. So if you're used to looking at a climate model, such as the community atmosphere model in CESM, we're currently at version 6. By the time we get to CAM 7, it's probably going to look something like this. We have CAM physics, we have MUSICA aerosols. We're coupling that to the spectral element dynamical core. This is just an example. Nothing has actually been determined about what's in these things or even what dynamical core we're going to use. It's just an example of a hydrostatic dynamical core that is on a not lat long grid that we're working with right now. You can also have a polar configuration. This, for example, will show an example of this that actually uses the regionally refined grid with the spectral element dynamical core, has CAM physics, has the aerosols, MUSICA aerosols, which are basically the MAM4 aerosols that many people are familiar with from CAM. We can also run chemistry. So this would have a more advanced chemistry package. It might also run in a regionally refined mode. And Mary's going to show some examples of this as the MUSICA version 0 model, where it's refined over the continental United States. You could also run a geospace model, and Han Li will show some examples where you're coupling to now plasmasphere and thermosphere models. You might also actually use data simulation to look at particular events. That's still forthcoming. We'll talk about that. And finally, you can also configure this as essentially a mesoscale weather forecast model with data simulation, a non-hydrostatic dynamical core, in this case MPAS, and physics such as WRF physics that's traditionally used for weather applications. And all these things would be available in a common framework. So obviously, we're not quite there yet. SEMA is a small project, and we're making advances by leveraging other work and complementary science goals. If you look on the website, you can see more details of the history, but we started as an internally funded project in fiscal year 2020. That was sort of SEMA version 0. We had a workshop in the summer, virtual workshop in the summer of 2020 to get community input and to help define the vision for SEMA. We've continued with internal funding in the last fiscal year. That's sort of the SEMA 1, version 1 development. That's a lot of what we're presenting today. And we've got these applications in development proceeding. We're also going to talk about the future. So the critical issues are we're moving towards convective permitting system. This has been challenging, as we'll indicate. And we're building a culture of development across communities. That's both internal and external. Inside of NCAR and with the larger community, that's equally challenging to some of the technical things that we're doing. We're also going to talk about what's happening now and into the future. We're looking at application targets and preparation now of a 3-year plan, again, hopefully with some internal funding to keep this moving forward. So this is the acronym slide. Mostly what we're going to focus on today is science developments, but it's and applications, but it's enabled by the infrastructure. So I call this the acronym slide because there's a whole lot of acronyms on it. These are the sorts of things we've actually been doing in the last year. So we've coupled a geospace model to WACM-X, so that requires working with the geomagnetic grid. We've got a non-hydrostatic dynamical core, the MPAS core, integrated into SEMA. So this is CAM MPAS. It's running now in an Earth system model. We'll show some examples of that at a variety of different scales. We've been pushing the envelope, and that's meant a lot of work on weak scaling corrections for the SEMA infrastructure. By the SEMA infrastructure, that really means CAM, SEAM, and even all the way down to ESMF tools that need to be able to scale to extremely high numbers of grid columns and large core counts. We've been implementing a new physics interface and new interfaces. This is the Common Community Physics Package, which is also jointly developed with NOAA. And we've also been developing into that a new object-oriented chemistry aerosol interface. Along with this, there's been work on GPU acceleration of the science code, both the physics and dynamics, and containerized versions of this infrastructure through CESM. So there's been some software engineering and technical developments and performance developments as well. And we're also working on planning for data simulation with SEMA, focusing on two of the systems that are commonly used at NCAR and in our community: DART, the Data Simulation Research Testbed, and JEDI, the Jordan-Anford for data simulation integration. We're not going to talk too much about data simulation, but we're happy to talk more on the discussion in question. So how do we actually work with all this? Well, at the core of SEMA, there are 4 science co-leads for weather, climate, chemistry, and geospace. So that's Bill, myself, Mary, and Han Lee. We set the priorities and coordinate across topics. We're also coordinating with management in the community and working on communication and outreach for the project, two-way. We also have, as mentioned, Jordan Powers, who's our software engineering project manager, and he's helping coordinate all these development efforts across labs at NCAR and with some help from the outside community. So we take input from a large group of people. So on the one hand, we have extensive community input. There's an external SEMA advisory panel. This is new. There are 8 members of that, 2 from each of the different science areas. They've met twice this year, and they've been very helpful with being a sounding board and guidance in shaping the project. We also work with the WRF, MPAS, and CESM working groups, tightly integrating and coordinating with them. Work both ways. So making sure that their needs and goals are also reflected in the SEMA plan, as well as the SEMA needs and goals are elevated in their development plans, and also the broader community. And that is to mostly set the science applications and to set the vision and let everybody know what's going on. And we do the same with NCAR staff and NCAR management, and all that feeds into our plans and the development efforts, which then result in the software engineering and the coordinated SEMA development. The current applications that we're going to talk about today are in various stages of being finished. And some of these are really exciting in different areas. They're not done, but we're going to show some really nice progress, I think, today. On the weather side, we pushed down to 15-kilometer global non-hydrostatic models, and we've got a 60-kilometer global and 3-kilometer refined mesh over the United States. These are both in development. For regional air pollution, there's a 15-kilometer refined mesh model. This is sort of the MUSICA version 0 over North America with chemistry. This is initialized, and there's some simulations that are available. There'll also be some tutorials starting later this week. And that grid is shown in the upper right, this CONUS refined mesh here. And then for climate extremes, we've been working on a refined mesh over the US and over South America. ComSets are in development for that. There's grid tools that are available to build these grids with the SC DICOR, and some simulations have started. And I'll talk about, this is Patrick Callahan's work. This is a grid mesh over South America that he's pushing down to 6 kilometers, for example, and comparing it to WRF simulations as part of a project we'll talk about in a little bit. There's also been work on coupled space weather, where the WACMX has been coupled to Gamera, which is a geospace model, and Han Lee will talk about simulations with that. And then Adam Harrington will talk about the 25-kilometer refined CAM spectral element Arctic coupled model with Greenland. And this shows a little animation of that. You can see this square has a refined mesh, and these streamers are actually getting a lot more detailed and higher resolution as you get into this region. And this is coupled to sea ice oceans in an ice sheet model. There's quite a lot happening, and it's in various stages of development and the ability for us to get it out to the community. So what's new about this? So most of these applications have been done before, but what we're doing actually with SEMA is we're pushing an envelope with an ESM, and everything we're going to show is basically happening in the same framework with the same modeling infrastructure, which is the goal of SEMA. So we've got a non-hydrostatic dynamical core and an Earth system model. We're pushing this down to cloud permitting scales at 3 kilometers. With horizontal meshes for weather and climate science applications, starting with regional. So that's regional weather and regional climate, and going up eventually to global. We have high resolution, fully coupled polar experiments, as I said, with coupling to the ocean, sea ice, and ice sheets. high resolution air quality and chemistry climate applications, coupling to geospace models on magnetic grids. And throughout all this, we're trying to do this again in the same infrastructure, and we're improving the infrastructure to enable the science. So we've got high performance computing scaling things we're dealing with. We're connecting to physics. There's GPU accelerators that are being brought into play, and we're using object-oriented program methods for this. And we're also trying to build a usable framework for the community out of all this. So this is not a model that we're just going to play with internally at NCAR, but this is designed to have workflows that will be usable for other people to do experiments and be engaged in development. So this is also advertising for you to collaborate with us, really. And I think that's going to stop the overview. Now we're going to talk a little bit about a series of different experiments. And I think on behalf of Patrick, I'm going to present a couple of slides on the South America regional climate and some of the grid tools that he's developed. So what Patrick's been doing in conjunction with the South America Affinity Group of the Water Cycle Project, which is an NCAR and community project that's been looking at high resolution simulations. They did work, the Water Cycle Project did a lot of work on snowpack in the Western US. And now they're taking some of those same tools with regional modeling and trying to look and understand South America climate. So this is a really large and complex region, including the Amazon and the cone of South America. And so there have been WRF simulations done down to about 6 kilometers that are sort of nudged at the boundaries. And Patrick has developed a similar version of this with a SIMA configuration of CESM. So it's a hydrostatic refined mesh model. This is 120 kilometers, 25 kilometers, and 12 kilometers with CESM. They're doing year-long simulations for several different ENSO periods. So different states of ENSO to look at the climate over South America. And you can see what happens as you refine, you get a lot more detail, you get a lot of big changes in precipitation structure over the Andes. And then this has been pushed all the way down to 6 kilometers. So these are 6 kilometer simulations, both at 32 levels and at 70 levels. So these are now being run for these multiple years, and the simulations will be available to the community as that progresses. And you can see there's quite a bit of detail here, and you get quite tight, quite tight coupling and tying of the precipitation to the actual Andes Mountains here, which is shown in the topography here. To do this, Patrick has developed a toolkit for building variable resolution meshes. This is designed to work with the spectral element dynamical core, will probably be extended in some ways to be able to work with MPAS. This is available on GitHub. We'll have a link to this on the webpage, SEMA webpage, but it's not there yet. And this allows for the generation of arbitrary grids for the spectral element dynamical core with control over regions, levels of refinement, and assists with creation of the data sets that are necessary to get these models running. So it's been a great, and it's done with a graphical user interface. So it's been a great tool that Patrick's developed that is usable, and there's some tutorials also available for that. So Adam, if you're available, there's Adam.
I'm here.
Why don't you take it away and just tell me when to advance the slides.
Yeah, sure. So I'm just going to give you a quick overview of some results from the polar grids and its availability to the community. Some of my colleagues are listed there. So yeah, go ahead and advance. The top left box, I'm just showing that we have 2 grids that are supported right now in CSM 2.2 or later, the Arctic and Arctic GRIS grid, which are shown in the lower right, where the Arctic obviously refining the top panel of the cube sphere to a 1/4 degree, and the Arctic GRIS the same, except an additional refined patch over Greenland up to 1/8 degree. And the top right is a nice little snapshot of a visualization we put together of the Arctic GRIS grid. So that's the 1/8 degree run. So you can see how it captures the nice orographic precipitation sort of splashing onto the southeast coast of Greenland there. To put these resolutions in perspective, the lower left, a big focus of these Arctic grids for me personally is representing the Greenland ice sheet and its surface mass balance. And what is shown in the lower left is on the y-axis, it's the average grid spacing for a number of different grids. The first category is your sort of typical 1 or 2 degree grids in CSM. You can see the grid spacing over Greenland goes from 60 kilometers to 160 kilometers. Our VR grids in the purple and the pink, the Arctic and Arctic risk grids, are about 27.8 and 14 kilometers. And the black dots are a RACMO regional climate model, which tends to produce a very truthful looking surface mass balance. And as you can see, we're starting to approach the resolution of those grids that are used for verification. And, you know, I just want to say that we have a nice workflow for generating surface data sets, such as the Greenland ice sheet ice mask, such that there's actually a very small difference in the actual area of the Greenland ice sheet across this huge variety of grids. And so that is a nice feature that I think we actually owe to CLM for creating great tools to do that. The top left is sort of some expected work in the future. So we have an Antarctica grid, quarter degree, called ANSI. And that is being worked on by colleagues at CU, Jan Lennertz, and his student Tridata. And we're hoping to have that released in the summer of 2022. I'm currently working on coupling the quarter degree Arctic grid to POP and the sea ice model that Andrew had alluded to earlier. And that should also be available next year. So I'm just going to show some select results in the next slide. So the left side of the panel is all these, F-case runs that I've done, that is fixed prescribed SSTs. And then the top left is showing you, the main source and sink contributions of mass to the Greenland ice sheet, precipitation and snow, and all the different colors are different model resolutions. And the black is the RACMO. And so what tends to occur with precipitation is you actually, these lower resolution grids produce too much precipitation across the ice sheet. And the VARES grids, which are in pink and purple, give a more reasonable, smaller precipitation rate, more in line with RACMO. And if you look at the map of the biases on the bottom map plots, with the left plots being these coarser grids and the right two plots being the VARES grids, you can see the reduction in the bias, in particular over the southern half of the Greenland ice sheet. And so that represents the improvements. Additionally, if you go back up to the line plot, the bottom panel is showing the melt as well, and these coarser grids tend to melt too much. The VARES grids are doing a much better job. And, as a rule of thumb, it seems that the coarser grids actually end up getting the total surface mass balance right because of offsetting errors. They dump too much precipitation, and then they melt too much precipitation. And so the net result is you can get a decent looking surface mass balance for the wrong reasons. And so the VARES is giving us an opportunity to do the surface mass balance correctly. Switching over to the right-hand side of this this slide is some results from me coupling the Arctic grid to the ocean. And so I had to do quite a bit of cloud tuning. I also tuned the snow over sea ice albedo to get a balanced top of the atmosphere radiation budget. And so there you see 150 years of running with a pretty stable rest on. About halfway through, I started to finally get the ice sheet model with the correct parameters. And so the bottom plot shows an 80-year run in blue. And that just shows what the actual total mass balance. So it's the surface mass balance, including calving. So it's a dynamic total mass budget for the Greenland ice sheet. And then the gray is sort of more or less a target that it's called the JGBG spin up. I won't get into it, but generally there's lots of anecdotal evidence that during the pre-industrial, the Greenland ice sheet was in a state of mass balance. And so it's really ideal to be able to run this pre-industrial and have a neutral or around zero mass balance. And as you can see with the blue line, we're starting to get there. And so we're just about ready to branch off and start running this over the pre-industrial, and over the historical period. We're going to do some ensembles over the historical period, and then we're going to run it into an SSP scenario for dynamic projections of the Greenland ice sheet. Next slide, please. So this is just some pretty snapshots of the Arctic grist grid showing that you can resolve the surface mass balance, the narrow ablation zones. You can resolve these katabatic wind features accelerating down the slopes of the Greenland ice sheet. And this is to entice anybody on the call who is interested in doing some analysis of these community simulations. Please email me at the email address below if you're interested in being part of this work. Back to you, Andrew.
Great. Thanks, Adam. That's great. Bill Skamrock is up next. He's going to talk about CAM impasse and the non-hydrostatic dynamical core.
Thank you, Andrew, and welcome everyone. Andrew, why don't you advance the slide here? The impasse dynamical core comes in as a managed external, which means it's being pulled into CESM and CAM from its own external repository. And about a year ago, we got to a point where we could start testing it. All the connections were set. And what you're looking at in this first slide is aquaplanet simulations, so full CAM 6 physics. And we're just looking at the throughput. So the vertical axis there is simulated years per day, and so higher is better. And you can see that the impasse dynamical core is scaling with the other cores that are available in CAM fairly well until we get out to the very extreme edge of scaling. So, for example, the highlighted line here, that vertical dark line there, 25 columns per thread, that's getting very far out there for a finite volume model. And I want to point out here is that all the other cores are hydrostatic, whereas impasse is non-hydrostatic. So the takeaway from this slide is that we're not seeing any significant penalty for integrating the full non-hydrostatic dynamics. Next slide, please, Andrew. This slide here is looking at how impasse handles the transport of scalar species. So think, for example, chemistry applications, where you may see hundreds of tracers. And here, the vertical axis is time to solution, so lower is better. And you can see this particular configuration of impasse, and these two past slides, this has been on 1 degree meshes for all of these cores. You can see that not only is it reasonably fast compared to the other cores, but it also scales very well as we increase the number of tracers. So the takeaway there is that there doesn't appear to be any scaling issues as we go to applications where the dynamical core needs to transport lots of species. So from those past two slides, I can also say that tests we've done in the standalone impasse, that's also available to run in just atmospheric mode, we're seeing results that are consistent with tests we've done in standalone impasse. Next slide, Andrew. So more recently, we've been pushing these aquaplanet simulations to much higher resolutions. In the standalone impasse, we've been running, for example, 3-kilometer global for very nearly a decade now, and now we want to bring that capability into CESM, into an Earth system model. What we've done so far is a series of tests where we bootstrap this to get down to higher resolutions in aquaplanet. We started at 120 kilometers, run out almost a year, and then at day 300, we dropped down to 60 by interpolating from that 120 kilometer solution down to the 60 kilometer mesh. We integrate. We've gotten down to the 15 kilometer mesh, and this is around 2.6 million columns to tile the sphere. When we try to go further, we're starting to run into some of the memory scaling problems that Andrew mentioned early on in the introduction. We have solutions to those that are being implemented now, and hopefully in a couple of weeks, we'll be able to get down to 7.5 and finally the 3.75 kilometers on the globe. To give you an understanding of what that means, 7.5 kilometers means we're about 10.4 million columns to tile the sphere, and 3.75 gets us over 40 million. And that 3-kilometer mesh gets us to over 60. So we're really pushing the envelope on the infrastructure, and we're making progress. but we're encountering some issues, and those issues are being addressed as we encounter them. Next slide, please, Andrew. So here are just some results from Aquaplanet that show you they're working. When we look at the globally average precipitation rate, this is for the full 360 days, and the different colors are the finer meshes that we bootstrapped down. You can see that they all produce in that left-hand plot a similar amount of precipitation and variance of that. When we look at just the convective precipitation, we can see that the component coming from the deep convection scheme, the Zhang-McFarland, is dropping off as we go to higher resolutions. This is expected given our understanding of how that works. The other dynamical cores show the same thing. And this is also tunable. From the weather side, I can tell you that this was somewhat of a surprise to me, but that we understand that, and we can potentially tune to change that if we wish. Next slide, Andrew. This is just the total precipitable water to give you a picture of what it looks like on the 120-kilometer mesh. Of course, it's very smooth with most of the moisture around the equator. Next slide, Andrew. When we go down to the 15-kilometer mesh, you can see that there's much more structure. And if you look around the equator, you can also see, for example, a hint of a double ITCZ, which is definitely in the solution when you look at other metrics. And this is consistent with what the results are from the other dynamical cores. So this is what we expect. So our next steps are to, when we get the fixes for the weak scaling, to move to the much higher resolution meshes that will get us to where we want to get very soon. Off to you, Andrew.
Thanks, Bill. So I'm going to talk a little bit about some of the other things we've been doing. This is CAMAMP has climate simulation. So this is 120-kilometer resolution. So back to the low climate resolution. These are 5-year simulations, and we're just doing some comparisons of CAM-MPAS, which is the red, to basically the default CAM6 with the finite volume hydrostatic core. And then there's some comparisons on the left for liquid water path and cloud fraction from the series satellite instruments, just to kind of guide you, showing the variability. Basically, the message is, and this is work that I've been doing with Xingying Wang at NCAR. Basically, the indication here is we're actually producing reasonable climates. There are obviously some differences here, but we made no effort to actually adjust anything or do any tuning of the model to accommodate the new dynamical core. We just run it, and we're basically getting very, very similar climate simulations. You can look at the dynamics too, which is probably a more useful comparison. So on the left this is the finite volume core. This is just the zonal wind. And this is the MPAS zonal wind, same thing. They look very similar. On the right panel, I've taken differences from an ERA interim climatology, so reanalysis climatology. And yes, there are differences, but it's not actually clear that MPAS is any worse than the finite volume core. There's some differences in the tropical structure, and MPAS is actually closer to ERA interim up at higher altitude. So it seems the dynamics also seem to be performing well. This took some adjusting of settings and basically making the MPAS settings for things like the damping at the upper level sort of match what we traditionally use in the climate model, but it's performing well and seems to produce perfectly reasonable climate simulations. Perhaps some more exciting things are some recent work by Xingying Wang, who's been pushing forward with some really great help from Bill and Miles Curry, also at NCAR, towards convection permitting resolution. So this is a refined mesh version of the MPAS core now, which is 60 kilometers over most of the planet and refines to 3 kilometers over this region of the Western United States and the Eastern Pacific, designed to look at atmospheric rivers. We've also pushed it up to 58 vertical layers, up to 43 kilometers. So this is a much increased vertical resolution. It's similar to basically what we think the next generation climate model is going to be, but it's also more similar to what you would use for a mesoscale model with higher vertical resolution throughout the troposphere. And that actually, these are recent results, but that actually seems to be holding together pretty well now. We're still working out some of the details, as Bill said, with the scaling issues, although this one, where you only refine to 3 kilometers over part of the planet, doesn't have as many of the scaling issues because it's a smaller number of columns. So it's pretty efficient to run sort of for regional climate type applications or regional weather. We have been playing with the physics at high vertical resolution. So this is what the sort of climate, the 120 kilometer, the total precipitation for a month. This is a January 2000 simulation of some atmospheric rivers for a month. You can see it's very smooth over the Western United States. You don't really see the Sierras at all. You see things impacting the Cascades, but it's all merged into kind of one mountain range over the West Coast. And when we put in high resolution topography and we run it at 3 kilometers, you see discrimination of the 2 mountain ranges in the West Coast. You see precipitation down in the Sierras now, though most of these rivers are hitting the Pacific Northwest. But we see really good, and then a representation of also snowfall because we're getting proper height elevation on the mountains. So again, this is running the CAM physical parameterizations at 3 kilometers in a non-hydrostatic mode over some pretty extreme topography. And it seems to be holding together. We're pretty excited about those simulations and how far we've been able to push it right now. And I think I'll turn it over to Mary.
Thank you, Andrew. So I'm going to talk about 3 things quickly. I'm going to begin with the model independent chemistry module and what that is and how we will take that to a box model that we call Music Box. And then I will talk about MUSICA version 0. So could you advance the slide, please? So the model independent chemistry module that is basically the idea of starting with a database of information about the chemistry, whether it's reaction rates, the reaction mechanism, properties of the compounds, or even the photolysis rate data, taking that database and creating the Fortran code that will become the chemical solver. And that chemical solver will be hooked into a standard interface that can hook with any atmosphere model, whether it's CAM or MPAS or any other model that's out there. That is our goal, including a box model. And so we have been working with the box model, and that we call Music Box. And let me tell you about that on the next slide. Thank you. So Music Box has now become available. You can get it on GitHub at that URL at the top. It's a mature version of the gas phase chemistry, but it's still a work in progress. It has basic gas chemistry. We don't have heterogeneous or cloud chemistry in it yet, but we are continuing to work on that. You can work with Music Box either via Docker HTML or command line and module executables for doing these simulations. And so shown in the big schematic is a screenshot of running this on it as an interface on the web via the Docker module. So, so you can see that you can use it like a GUI. You can see what chemical species are there. You can change the chemical species. You can add chemical reactions, change the reaction rates, and you can run the model, plot the results, and you can even look at graphic pictures of the chemical reactions for a particular trace gas, and that's that little ball and spoke graphic shown there. So besides improving heterogeneous chemistry, cloud chemistry, we're also starting to design interfaces for the aerosol processes. So that's Music Box. Like I said, it's available on the web, and we'd be happy to have people try it out, test it, give feedback to us. So on the next slide, let's move to MUSICA version 0. MUSICA version 0 was released last year as part of CESM 2.2. It's a configuration of CESM. It's CAM-CHEM, the atmosphere model with the chemistry, using the spectral element dynamical core and regional refinement. So what you find when you have regional refinement, the emissions and the chemistry are much more accurately represented. The pollutants are now being simulated on a human exposure relevant scale, and we have the global feedbacks directly included. And then in terms of computational costs, it really doesn't cost much more, really doesn't cost really any different than, say, running a regional model over the continental US, because the number of grid points in the coarse grid area of the globe are not very many more to add in. So we've been doing applications with this, and I'll share a few of those on the next slide for this. So the initial application has been conducted by Becky Schwentes and Forrest Lacey. Becky has recently submitted a paper describing that work, and Forrest is preparing his paper. And so this is focused using the CONUS regional refinement. And I'm showing here in the upper right, surface ozone from a 1 degree global simulation and the regional refinement simulation. And so you immediately see the detail that you gain in surface ozone over the United States. But I also want to point out what happens as you go off into the Atlantic to the east, and how that you still get improved resolution, you get a different answer to your surface ozone. So the regional refined area is affecting the downwind coarser area as well. In addition, if you click again, we have a application where Wenfu Tang, who's a ASP postdoc here at NCAR, is applying MUSICA version 0 to the US to study wildfire emissions. And so this is just, again, a plot of surface ozone over a region of the US where there are wildfires occurring, overlaid with the DC-8 flight track, and so that we can do comparisons with aircraft measurements. And then we've also have moved the grid to other regions of the world. And so the next click will get us a view of the grid resolution that Dusong Jo, another ASP postdoc, is doing to study air quality in Korea. And so, and then if you click again, we have one more application I want to share with you. And that is that we, over the past year, have begun simulations with MUSICA version 0 to look at Asia in support of the Asian Summer Monsoon Chemical and Climate Impact Project, ACLIP. And we're comparing that here in these plots with the WACM model that's more at the 1 degree grid resolution. And so this is carbon monoxide at 100 hectopascals, so in the upper troposphere, lower stratosphere region. And you can see how different the convective transport of CO is for the coarse grid resolution on the left versus the finer grid resolution of, I think this is just at 25 kilometer grid resolution. So there's quite a bit of gain in going to these finer resolutions with the regional refinement. And this work is being led by Ren Smith, who is also here at NCAR. Okay, so next slide. And I want to talk about the community music version 0 simulation that we are providing to the community. So this is using our CONUS regional refinement region, and the configuration of the simulation is outlined here in terms of the emissions being used, and the fact that we're also using carbon monoxide tags, so we can tag different anthropogenic emission regions, and we also have a biomass burning CO tag. And we've done these simulations for 2012 and 2013 so far. That was mostly my push to look at convection from the DC-3 field experiment and the Seekers field experiment. There are a lot of field experiments during that time period that make this a very useful simulation. So we have output for a variety of timescales, monthly, daily, and hourly averages. There are many chemical species and meteorological variables available. And it includes a time series files with a single variable, a single chemical compound. That output is now available. You can reach it via the SIMA webpage. And we're going to help the community learn how to use MUSICA version 0. We're going to begin a tutorial series starting this Friday. This Friday's tutorial is about plotting and analyzing output from regional refined grid meshes. And so that's what we're offering, and I'd like to pass this on to the Geospace section.
Thank you, Mary. So I will give an update on the Geospace. Next slide, please. These are the main Geospace development. The spectral element dicore now is species dependent, and that's the main development in the last year. And the regrading scheme has already been developed with V0, but it was used for finite volume at that time, and now we're using it with the new die core. So with those, we are testing the high resolution Wacom-X SE capability, and I'm going to mainly show the result from that. And in the CSM workshop in June, Kevin Fenn has showed an update on the one-way coupling between Wacom-X and the Gamera MHD code, and I will not go into any details there. Next, please. So this is the model setup for the high-resolution Wacom-X. Apart from the species-dependent spectral element die core, we've also added the molecular viscosity and diffusion in the horizontal direction, and vertical has always been there on the physics side. And we turn off all the gravity wave parameterization so we can evaluate the resolved wave impact. And as in previous Wacom-X, we have interactive ion and neutral chemistry, and also interactive ionosphere dynamo, transport, and energetics. And all this, of course, is mediated by the regradient scheme. And the model extends from the surface to the upper thermosphere, and it's on a cube sphere, and the resolution is 25 kilometers. And for the released data, it's interpolated on a quarter degree grid. And for the vertical, it's 1/10 of a scale height vertical resolution in most of the middle and upper atmosphere. And we have run the model under constant solar conditions and also geomagnetically quiet conditions. So far, we have completed 2 months. That's the data we're going to release, or we already linked it in the website, and it's still running right now. Next, please. So from the simulation, we have found a very profound gravity wave impact on the thermosphere circulation. And here we show the zonal mean zonal mean forcing and by gravity waves, and also on the right is the meridional forcing. So you can see that in the thermosphere, there's a predominant eastward gravity wave forcing, larger in the winter hemisphere. And the meridional forcing is mainly counter or against the summer to winter circulation, so southward, and also it's larger in the winter hemisphere. And the magnitude are quite large, over 100 meter per second per day. And if you compare to the large-scale eddy forcing, one click please, which is on the lower part, that's the total forcing. You can see that the dominant large-scale forcing, mainly from tides, is westward. So this provides, the gravity wave provides a significant modification to that. And both the zonal and meridional forcing provide a very strong force to slow down the summer to winter circulation. We can't check the realism because there's very, very limited observation of global observation of thermosphere gravity waves, and but the circulation is closely tied to constituents. So next slide, please. We know that from our previous Wacom-X simulations, coarse resolution, regular resolution simulations, we always overestimate the O2N2 ratio and compared with observations. And you can see in the center panel, which is a lower resolution run, latitude and longitude and latitude. And you can see that in the winter hemisphere, the O2N2 is very, very large, over 2, the ratio is over 2, or over 2.5. And now the left panel is the high resolution results. So you can see now the O2N2 is much reduced. If we look at the latitude profile of the zonal mean O2N2 ratio, this is column integrated, and you can see that the winter peak drops from 2.5 to 1.6, which is much more consistent with observations. And one click, please. Yes. So along with that, we also see other changes in major and minor species. For example, we see changes or increase in the global average O2 number density, nitric oxide, and a decrease of the F region electron density, mainly from O+, and the increase of the E region, NO+. Next slide, please. And then along with that, we see a lot of changes in the energetics. We see that the total shortwave heating on the left, upper left, and the total long-wave cooling both increases as a result of this change in the constituents. And two quantities of particular interest for us. One is geoheating on the lower left, and one is no cooling on the right. And again, this is at winter hemisphere at higher latitude, and in both cases they show increase. Next, please. And then we look at the perturbations. Andrew, you can just click on that. Yeah, let it play. Thanks. And we look at the perturbations to neutral and neutral atmosphere and ionosphere. So on the left is the perturbation to the zonal wind, and the main thing I want to point out here is the eastward tilting when you go upward. This is in the equatorial region, and this is consistent with the predominant eastward forcing we saw in the zonal forcing. Another thing is that recently with the ICON, they have shown that this feature very similar. The ICON wind measurement, they clearly show this eastward tilting in the thermosphere. So this is very consistent. On the left, on the right, we're showing the relative changes of the total electron content that's been filtered for only retain the high frequency component, a period less than 2 hours. So you can clearly see this a very clear wave signature, and again stronger in the winter hemisphere in the north, and also it is strongly modulated by the wind, thermosphere wind, which is strongly dependent on the local time. Next slide, please. So those are the V1 development. There are currently two important development activities. One is led by Kevin Fan, work on the two-way coupling between WACAM-X and Gamera. So this is an important part of the HAO's effort to develop a whole geospace model. And also it is part of the MAGE model, the multi-scale atmosphere geospace environment for the NASA CGS Drive Center. Another development is mainly done by colleagues at M-Cubed, led by Bill Skamrock and Joe Clamp. And they have laid a kind of groundwork for a deep atmosphere dicore. They extended the MPAS to the numerics for deep atmosphere in MPAS. And also they took a SLAP version of the MPAS and extended into the thermosphere. And with that, more recently, they have implemented a constant pressure upper boundary condition, which addresses major issues associated with fixed height boundary condition because of the very large thermal expansion and contraction during day and night and during magnetic storms. So those are the things we're going to work on in the next couple of years. I think that's it for Geospace.
Thanks, Hunley. So we're almost at the break. I just wanted to summarize everything we heard with some of the SEMA configurations that are available. So this is an image of the website, so sema.ucar.edu. And right at the top, under a brief description of SEMA with the schematic diagram, is this section on SEMA configurations and simulations. And so available there now, there's discussion of the polar climate configuration, actually how to actually run that configuration that Adam has provided. There are links here under chemistry to these MUSICA V0 simulations, and there's a description that Hunley just provided for the geospace with the thermosphere and the geomagnetic grid. And we'll also get, it's not up there yet, but we'll get links to the grid tools and some of that information that's available also that I showed. So Those are all available on the webpage. You can go back to that. So again, there's polar, chemistry, geospace, and the climate grid tools will be up there. Everything else we showed is in development. We got a strong message in talking with the community that we don't want to let things out in the wild that are not really stable yet. So a lot of the stuff is still in development, but we are interested in collaboration. So please contact your friendly SEMA lead. And we would be happy to explore what the science needs, science interests are, and where there is opportunity to get sort of early stage access to this. But it really is a development model. We are pushing the envelope, and we come up with all kinds of things. So if you're interested in doing development, please let us know. So we're going to leave this up, and I think we're at the break now. We're going to take a 10-minute break. So we'll come back about, let's call it 10:07 Mountain Time. And if there are questions, that link should be there and in the chat. Can everybody still see that link in the chat? Hopefully. And then there's also a Google form that's available for comment. We're not really going to deal with that feedback now, but we'll deal with that feedback later if it's more extensive. So I can see the questions in the chat coming in. And we'll be back in 10 minutes and take those questions for discussion. Then we'll launch into a brief discussion of what's happening for the future with SEMA and wrap up with any comments and discussion of that at the end. Anything else that any of the co-chairs want to, or Elizabeth, any other technical things we need to deal with right now before we send everybody off? Okay. If not, we'll see you in 9 minutes now. So thank you very much.
Hi, for anyone who's just joining us, we're on a break and the presentations will resume in just about 1 minute.
Great, we see it.
Okay.
Okay, let's get started. Welcome back. And we'll do the question first, the Slido questions. So I will read the questions and then assign it to the experts. And so we'll get the first one out as the second one. Will the slides be shared later on? Yes, it will be, and through our website, I think. Okay, we can get rid of that question. So the first question here is how easy it is for users to create their own variable resolution grids and the related input datasets for SEFV3 and/or MPass for specific science applications. That may be a question for Patrick. Andrew, you want to take that?
Sure, I can take that one. So we're trying to make it as easy as possible. I would say it's not that easy right now. We've got the most developed tools for SE, basically. And some of those will work partially on FV3 and MPass, but it still requires pretty much an advanced user. So, and this is also related to the second question. There is, and I'll put this link in the chat, and we'll get it up on the SEMA webpage in that location. There is on the MUSICA website a tutorial that Patrick did earlier in the year that shows how to use that graphical user interface tool and how to install it. And as we had indicated in the slides, that's also, there's some basic README functionality on the GitHub page, which is located there. So I put that in the chat. So the answer is, it definitely requires an advanced user to construct all those grids. A lot of it is, there's a lot of different data sets right now. And one of the goals of SEMA is to make this whole process easier and more seamless, but it's not quite there yet.
For MPass, the meshes, all the meshes that are available in the standalone MPass are available in CAM, and that includes being able to move the refinement region on these meshes, with the understanding that anytime you bring in a new mesh, you have to be registered within the system within CESM so that it can talk to the other components. So all the existing tools do work.
If I
Thanks,
could just quickly add as well, this is Adam. I've walked maybe a handful of different postdocs through the process of generating a new grid and all its data sets and installation. And you know, Pat's toolkit has pretty detailed instructions that if you follow them carefully, even if you're a new user and you're, you know, you can get through it in the matter of a week or so. So I have seen it done. If you're an expert like me, you can do it in a day. I'll stop there.
Thanks. Okay, if nothing to add, we'll go to the next one. Do you have, I thought it was topography. I think that one disappeared. But anyway, so this one is, do you have plans to run comparison simulations between results produced by SIMA and results from standalone models such as WRF and MPAS? Bill?
The answer is certainly yes, and Andrew alluded to this with, for example, South America, the work going on down there in the simulation with high resolution SE being compared to WRF. We plan to do the same for MPAS because obviously, while the dynamical cores may be the same, for example, MPAS and CAM, MPAS standalone, the physics are different. And we want to get those comparisons to understand how we need to tune and potentially change our physics. For example, here in CESM for the convection permitting simulations.
Thank you, Bill. So our next question from Julius Akinyula. How realistic is running SEMA with 3 kilometer high resolution, and how do you generate emission data from the chemistry module in SEMA?
I can I mean, as for realism, we're just starting to take a look at it. We've just gotten simulations in the last couple of weeks with a full topography and getting the physics running. So obviously from what I showed from precipitation, it looks pretty realistic, but Xingying Huang is going to be doing a comparison between those West Coast simulations I showed and WRF simulations doing the same sort of thing in a regional configuration. So we should have an answer to that question pretty soon, which is why we're not releasing that model yet, because we actually have to figure this question out. We can downscale the emissions data. That's what's the simple aerosol emissions data. That's what's been using now. I don't know, Mary, if you want to comment on other aspects of the emission data for the chemistry.
Yeah, sure. So yes, we can. So we have an emissions tool that comes along with MUSICA version 0, and that regrids conservatively the emissions for the simulation for the grid mesh. And when it comes down to, most of our grid emissions data sets, our best are 0.1 degree, right? So when you go to 3 kilometers, you have to do some downscaling and either make some assumptions or put up with, maybe not quite as accurate emissions. Obviously, point sources can be located a little bit better. We do this with WRF-Chem, and so we have the expertise, we have the emissions tools that will take us to that kind of grid resolution.
Well, thanks. Okay, so our next question is, that's the topography one. Is there available documentation for generating topography files for either refined SE or refined MPAS grids using CAM topo tools? Bill and Andrew, probably.
That's work in progress. That's work in progress, and we're trying to get there because right now the topo tools have really been designed for coarser meshes that have been used in climate studies, and so they're being worked on to work better with the very high resolution topography that we want to enable in our applications here in CESM.
Okay. The next question is for me. So is there a reason?
I'm sorry, Hanley. If I can just add.
Sure.
There is currently support for these SE refined grids to generate a consistent topography file. And the directions for doing that are in Pat's toolkit. So for SE, there is already a workflow. There's actually 2 workflows you can choose. That's all.
So is that also from CAM topo?
Yeah, so one of the workflows is to use the CAM topo software tools, and the toolkit will give you instructions on how to create the data set necessary for the topo tools to ingest in order to create a consistent refined mesh.
Okay. Thanks, Adam. So, question for me is there a reason why one should expect eastward forcing from gravity waves and westward forcing from tides waves during January in the thermosphere? I think tides, yes, especially migrating tides, is always propagating eastward. So we do expect eastward forcing from tides. The gravity wave, yes, it's a bit puzzling why it's always eastward. But we do have evidence for that when we do our parameterization exercise, because if we use a symmetric spectrum in our parameterization, we get the breaking level. This is for MLT, breaking level and jet reversal at about the same altitude. But you can see that in observations, both satellite and ground observations, the jet reversal level should be lower in the winter hemisphere. So the eastward reversal usually is lower, and the westward reversal is higher in the summer. So to get that, you need to tune up the eastward spectrum so that it will break at a lower altitude. I don't know why. Maybe this has something to do with the generating of the waves. But now it seems that the high-res model can reproduce that, and also the asymmetry in the jet reversal level. So we can look into that now with using the model. Okay, the next question, for the MPAS scaling studies, are you using, oops, I lost that question. Next one. Are you using improvements to the boundary exchange created as part of the GPU enablement work? Right.
Yes, and the answer to that is not yet in the CAM version. The version is brought into CAM. That will happen once we've done more testing with that and are bringing it over. And that's going to be part of enabling GPU capabilities in CAM and CESM that we're bringing in over these next year or two. So not yet, but it's coming.
Thanks, Bill. Oops. How computationally expensive is it to run the high-res WACAM-X SE? Oh, okay. So I think it's on the order of 10 million core hours per year. Yeah, I think that's around there. And usually when we run, there is a memory issue, so you cannot run. You have to run on certain using node numbers above certain values, so that you have enough memory for running the model. But yeah, so the cost is about 10 million core hour per year. Any plan on making WACAM-X Dart, or perhaps with JEDI data assimilation code public? Data assimilation. So I think WACAM-X Dart. Yes, I think maybe Nick would be better suited to answer this question. I think yes, it should be available. There are some technical issues with ESMF, I remember, and but once those are fixed, I think maybe it's already fixed with the new regrading scheme. Once that's fixed, it should be released as, but not for now, not as part of JEDI. Anyone want to add to that? Okay. We go to the next one by Pablo. Can we expect Patrick's refined South America grid to be stable for chemistry and air quality simulations? Mary?
Actually, I was going to pass it to Andrew, but since he's working with that more.
I think the answer is we think so, but with these complex models, you can always be surprised. So in theory, the chemistry is stable and it works. We know it works for North America. So if the simulation itself is stable for South America, then theoretically it should work for South America. That's sort of principle of SEMA, but that remains to be proven in this particular case.
And then the other step is to get the emissions, and that'll take an extra step or two to make that work.
Okay. Can spectral element advection be combined with the MPAS non-hydrostatic core? Bill?
Let me, so that's not a complete question in the sense that the spectral element advection on the spectral elements itself, no, because the spectral elements aren't defined on the MPAS icosahedral mesh, essentially. The other advection, C-SLAM, potentially could be, but it hasn't been generalized, again, to handle the MPAS mesh. So the two flavors of advection that are done within the SE core have not been extended to handle the MPAS mesh structure at this time. Should we potentially move on now to the future and then return to questions?
I think that might be a good idea.
Yep.
We can do that. We can answer some of these questions offline, or we'll get back to them in the further discussion. So I will, oh, I guess I just want to go back to sharing the slides, right, Bill?
Yes.
So the next steps. See how that works. There we go.
Okay, next slide, please, Andrew.
Oh, got to hit it on the right machine. There we go.
Thank you. So what I'm just going to go through very briefly here is our near-term plans for SEMA. NCAR is going to continue funding SEMA, but they're going to restructure that funding. And essentially, it's been going year to year for the past several years, and now they want to look at a longer-term commitment. Potentially, we're looking at 3 years to allow us to better plan and execute what we need to do to bring this capability to the community here. And essentially, they want to broaden or bring SEMA into a bigger picture of NCAR has for developing capabilities for Earth system science and a community of practice in Earth system science. And you'll be hearing that phrase and similar phrases coming out of NCAR as our future direction in the near future. And essentially, the directives we've been given from NCAR management is that they would like us to focus primarily on a single science goal, with the understanding, of course, that we're targeting a number of science goals, but they want our principal effort focused on a single science goal. And that single science goal, next slide, please, Andrew, is essentially to get down to convection permitting resolutions for looking at tropical cyclones and other aspects of tropical circulations in the Atlantic that affect the US, and also, for example, landfalling cyclones in the US. So that's our goal that we're primarily focusing on. In particular, we're trying to look at mechanisms of TC formation in the Atlantic, so that brings in aerosols and dust and other aspects of that on how these things form and how they evolve. And as I mentioned, the landfalling aspects of those tropical cyclones. I would point out the graphic here is just from MPAS 3-kilometer simulations, which we did almost a decade ago when Yellowstone, our supercomputer, first came online. We're trying to bring that kind of capability into an Earth system model so we can examine these more complex questions. Next slide, please, Andrew. So in a nutshell, we're trying to get to convection permitting simulations. As you've seen, we're dealing with issues associated with taking an infrastructure that's been developed for climate and bringing it to these very high resolutions, a cutting edge of climate and weather and applications that want to leverage that. That means we need to be able to get to order, something 40 to 50 million grid columns at the least to get to the right at where we can call ourselves convection permitting, where the deep convective parameterization no longer plays a significant role in our evaluations. And we have to have physics suitable for those applications. You've already seen a preliminary test we've done, for example, with MPAS with the CAM6 physics. It's stable, it runs, it produces results that are believable when you just look at a quick first look. but we've got a lot more work to do to verify, tune, and perhaps change some of the characteristics of those physics. We'll see. And also, there's lots of work to do because now going to much higher resolutions, we've got to bring emissions and everything else to those much higher resolution grids. So that's our goal that we're focusing on within the context of tropical cyclones in the Atlantic, although here we're looking at a tropical cyclone in the Pacific. Next slide, please. So essentially, our pathway here is that when we have addressed those scaling issues, the memory scaling issues, and some other issues we know are there, we hope to have those addressed in the near future, weeks to months for some of these. Certainly, our first efforts will be to get to non-hydrostatic scales will be with the MPAS 15 to 3 kilometer mesh. We have lots of experience with this outside of CAM and standalone MPAS. We're trying to bring it into CAM and run it. And that 3 kilometer meshes we have in these variable resolution configurations cover, for example, North America, or you can shift them wherever you want. So we expect we'll be using those with field programs, for example, the recently CPEX, which was going on in the Caribbean. And certainly ACLIP, we have ideas we want to use it there too. We've got a lot here to do. We've got to develop tools that allow us to have workflows that are manageable for these very high resolution meshes because the data sets get a lot bigger. We need to be able to develop DA tools to use within CESM and MPAS because essentially DA at its first implementation allows us to get a direct comparison with observations in a statistical manner, in addition to then moving on to cycling data assimilation, which we'd like to do. And as part of this, we also see ourselves doing simulations that are longer in time, going over months and seasons. We also see ourselves doing ensembles and sensitivity experiments as part of this first goal that we have. And MPAS and the other dynamical cores already work with DART, so they should work with the DART implementation that's currently in CESM relatively seamlessly, but we're also working on bringing JEDI capabilities into CESM. Next slide, please, Andrew. Obviously, this is a common infrastructure that we're developing, and with this target we have of looking at tropical cyclones at convection permitting resolutions over the Atlantic, that capability is going to give us the capability to address a lot of other problems downstream. For example, we can go to high resolution in the Western Pacific, where, of course, questions revolving around the MJO and ENSO and everything else are critical. One thing we certainly will be looking at is convective environments over the US and how future climates will change that. And the high resolution will give us an ability to directly look at severe weather in those environments, in those different environments. We're developing that technology will allow us to look at also, for example, WACM-X applications. That are a variety of those. As I mentioned, we want to bring these capabilities to other field programs, ACLIP, for example, and others that we see in the future, which hopefully will happen. Of course, it's been very challenging with field programs these last couple of years with COVID. Hopefully, they'll be getting on track more. And then finally, for example, the other applications we want that we've been doing outside of CESM at very high resolution, we want to bring inside to this Earth system model, urban air quality, much more data assimilation. And certainly we also expect that we'll be applying this system to other planets and exoplanets, for example. So all of those capabilities we see down the road, and our focus on a particular capability should be very straightforward to leverage to these other capabilities as we go into the future. I think that concludes things, and we should move back to the discussion. I encourage everybody, if you have questions or comments on this, please use Slido, and we will address those questions.
Okay, so I'm moderating this, and So I'll read the questions and pass it on to my co-leads. So the first question is, how was this primary science goal chosen? Bill, do you want to answer that?
Thank you, Mary. This was chosen as a discussion between essentially the 4 science leads and scientists in the labs that we have been talking with, and NCAR management, the director's office. And so and we've been working with the director's office over the past, probably almost 6 months now on this, not a change in direction, but this refocusing and this setting us up for a longer term future with 3-year funding and hopefully increased funding that will produce.
Thank you. So with this main science goal of simulating Atlantic tropical cyclones, ocean coupling seems to be essential. Is SEMA developing the coupled Earth modeling system as well? And the answer is, this is why we want to get MPAS in CESM, is to hook to the rest of the Earth system, and especially have this coupling with the ocean. Bill, I don't think, do you have anything more to say?
Well, so SEMA is primarily focused on the atmosphere. So the coupling with the ocean, we're not developing it in as much as we're inheriting it from the current system.
Yeah.
As we go to MOM, as we transition off POP into MOM, we're inheriting it. I think many of you are possibly also aware of the Earthworks project led by Dave Randall up at CSU, which we're working with jointly with us at NCAR, and that's going to bring in the MPAS ocean. So there's going to be an interesting mix of capabilities along those lines coming to the fore in the near future. That will also highlight GPU capabilities, which is the next question here on Slido that I'm seeing. So the GPU capabilities are going to come to the Earth system model and not just the atmospheric component.
Right, so let's continue with the GPU question. And I'm going to say from the chemistry side, we're starting to explore looking at GPUs to do the solving of the chemistry. And some groups out there are moving right along with this, and we're trying to partner with that. Andrew, do you want to add to the GPU question?
Sure, Mary. So we talked already about that we're going to be we will eventually have there is a MPAS, a version of the MPAS die core that is GPU enabled. By GPU enabling, it means mostly at least for the physics and dynamics, we're using putting ACC directives in the code. These will work on the next system, Derecho, which is going to have a certain proportion of GPU capability at NCAR, and we'll work on other systems as well. So we're also pushing forward. We have a version, we're pushing forward with the physics. So we have a version of microphysics that runs on GPUs, and we're building experience with that. And we're working with our computational lab to enable sort of heterogeneous architectures. And we're trying to make sure that the infrastructure we're building enables us to push as much of the model onto the GPU systems as we can.
Okay. And Hanli, do you have anything to add with GPUs, or are we finished with that question?
No, I don't have anything to add.
Okay, so let's move on. So the top question here is, how in the future will SEMA be more inclusive of the widespread community science needs when determining priority science goals? And so I'm going to begin and add on another comment because Bill talked about how we discussed it among the leads and with NCAR management. We also discussed it with our external advisory panel that represents the 4 subject areas. And I'm sure other people have more to add, but this is the challenge with SEMA, right? You need to focus on a particular thing, but you want to try to benefit the most science applications possible out there. And whether, but there are a lot of questions and a lot of exciting science to do. So choosing that one is really a challenge. I'm going to pass it over to Andrew, and I think maybe he can talk more about, future workshops or meetings or other ways that we can get community input.
Well, I would actually just point everybody to that Google form link, because that science goal that we identified is still in development. It is not necessarily final. So if you have comments on that, one of the ways we are shopping that in addition to dealing with the community we normally talk to, is having these sorts of meetings. And so your opportunity for comments on that goal are very much encouraged. So please use that Google form link or contact us directly if you have ideas or comments about that science goal, because we want to hear it. Let's see if we can look at the whole question now, because it was edited. Do I have to click on it? How do I expand it? Because I can't see the whole question. I can't actually see the whole question. Can anybody see the whole question?
Yeah.
Anyway, so I mean, the whole point is we are focused on the atmosphere, but the science goals are discussion for continual renewal. I guess I can take this next question about the community workshop last year.
Thanks.
The result of that, if you go look on the SEMA webpage, there is a whole vision document that has guided us for the last year on this development. And that's basically helped us set the science applications that we've been developing over the last year or 18 months or so. And this is, again, we're coming out with expanding that direction and being asked to focus that direction. So we're coming back to the community in this sort of environment, as well as through our networks and the external advisory panel, to continue to refine that direction. So it's an agile development process, even with our science applications and our goals.
Thank you, Andrew. Okay, so yeah, I guess I want to emphasize that please use the Google form to provide comments about SEMA future development, current development, et cetera. We think this will be a great way to get community input to directions for SEMA. So the next question is, it keeps jumping. Okay. Can you please comment on the advantage of using MPAS and SEMA for uncoupled weather applications versus standalone MPAS? Bill?
Well, I would say right now there is no advantage for using MPAS and SEMA if you're not going to take advantage. Oh wait, hold on, I read that wrong. In SEMA, you can couple MPAS with ocean and other components in your system model. This is huge. This is definitely huge. And understand, all of the major operational centers are going or have already gone to using coupled models for their flagship global NWP. That includes ECMWF, the Met Office. As usual, our own weather service is a little bit behind there, but they'll catch up eventually. So this is critical for research. Now, standalone MPAS, what you get with standalone MPAS is physics that has been tested and evaluated quite a bit more at these convection permitting resolutions. And that's what right now in SEMA, we've only just scratched the surface of how that physics behaves at high resolution. We know there are issues in that physics. For example, there's a team looking at the behavior of tropical cyclones at high resolution with the CAM6 physics. And they're looking to do some tuning to address some issues with how it depicts tropical cyclones. So standalone MPAS right now, if you don't need the coupling, you're going to get physics that run that are much better tested and give you more realism from what we know so far than what you will get with MPAS and SEMA. That's the main advantage of standalone MPAS right now. Plus the fact that it runs a lot faster, because when you go into CAM6 physics, that physics is much more extensive and costs quite a bit more.
And then just to add that so far this has been our pathway to get chemistry into MPAS. And so to achieve air quality studies, especially urban type air quality studies in a global context will be via SEMA.
Also, I want to quickly add that if you want to add the upper atmosphere physics and chemistry through CESM is the way to do it.
I'm going to jump to the, can we use MUSICA for aerosol cloud interaction studies? Because it's been sitting there a while and keeps getting jumped around. And the answer is that yes, we can use MUSICA for aerosol cloud interaction studies. And actually, I think it'll be an exciting application to be able to zoom in on a region where we can do a more explicit representation of aerosol cloud interactions and see what the global effect is. So yes. Okay, next question. Since SEMA is using the CESM framework, will it follow CESM and use NUOPSI?
Yes.
And yes, it will use NUOPSI and
It is.
the old coupler. It is, yes. And for example, a lot of the results we showed you were based on use of the NUOPSI coupler.
Yeah, most of the CAM-MPAS work now is happening with the NUOPSI coupling.
Okay, thank you. Next, are you planning to connect the SEMA efforts to the WCRP Digital Earth Lighthouse Activity Program?
Yes, so there are two Andys, myself and Andreas, Andy Prine, who is also on the call. We are both deeply involved in that WCRP Digital Earth Lighthouse activity, which is Digital Earth is sort of global high resolution modeling, comprehensive digital twin type approach of, it's very expansive, but Andy Prine and I have been involved in that for the last year or so. So yes, SEMA is pretty well aligned with that activity.
Great, thank you. So for farther in the future scientific applications, looking at past Earth states would be great. Worlds with higher and lower greenhouse gases and different chemistry. So first, I want to make a comment that this is a great comment to put into the Google form. Andrew or anyone else want to comment on this?
I agree. Paleo versions, deep paleo, it would be a great application for making sure that we can get the flexibility we need to do the right science, and an extension to, it's essentially another planet, but it's much more similar to ours. And
so I think, Andrew, you'll answer the next question too about SEMA being used for IPCC's climate scenario comparisons.
Yeah, this is a great question because I think answering it helps define what SEMA is and what SEMA is not. This group, SEMA, the co-leads, are providing infrastructure for models. That infrastructure will be inside of CESM. CESM will be running IPCC climate scenarios for climate purposes. It will make the decisions about how to configure SEMA for its needs for the IPCC climate scenarios. So the answer to the question is, in one sense, yes. In the other sense, we are not making any decisions about anything that is needed for CESM. And if CESM needs something out of the infrastructure, SEMA will provide it. So CESM is and that project will continue to provide IPCC climate scenario comparisons for SEMA, the coupled model intercomparison project, as necessary. SEMA as a project enables that, and SEMA's development needs to be able to support those efforts. So hopefully that clarifies, and I'm happy to discuss that further. So we're not making any decisions, and we are not running SEMA. CESM will run its own coupled modeling system. The atmosphere configuration will use SEMA to do that, but it decides how it does that.
And so the next question is whether there's a plan for supporting low resolution configurations of SEMA for paleoclimate and other very long-term simulations. And I think it's sort of along that same theme of deciding what the configurations are, because this is a modeling infrastructure that we're building. Please.
Right, Mary, and if I can answer that. So SEMA also envisions a suite and a hierarchy of simplified model configurations, which would include resolutions. It would include being able to run regional configurations down to large eddy simulations, single column, and idealize things such as aquaplanets, and even a convective equilibrium type simulation. So SEMA is definitely designed to support a hierarchy of models that the community wants, and low resolution configurations would be part of that.
Okay. So next, what is the timeline for delivering MICM in MUSICA? And I actually found that to be a challenging question because I don't have an answer that it'll be 6 months or 1 year or 2 years. Turns out there's a lot of things that we're working on and developing and testing. MICM generated Fortran code is one of our priorities to get done in the next few months to a year, in terms of testing that in a 3D model. But to have the full MICM in MUSICA and having MUSICA version 1 running, we see that as a multi-year activity. Sorry, I can't give you a more definite answer on this. Okay, next question. So how closely does the MUSICA version 0 model represent greenhouse gas sources, and what is the spatial resolution of these sources? And the next question is, what is the source of historical greenhouse gas emission data used in the SEMA model? So for the MUSICA version 0 model, the greenhouse gases are specified as surface mixing ratios. Those are based on observations or a scenario. The resolution is coarse. Generally, the zonal means are used for this. And since I don't do climate modeling, I think I'm going to pass this historical greenhouse gas emission data set to Andrew or
yeah, the historical emissions data set that we're using for greenhouse gases right now is just the standard one that is used from CSM, which comes from the standard sort of CMIP sources. We have different scenarios for that, and it uses the standard sort of CMIP recommended historical greenhouse gas emission scenario.
So I
would
think
say to you,
that,
yeah, the one comment is one of the things we are intending to do is develop a better emissions tool chain. I don't know if you want to comment on this, Mary, at all, if you want to comment, but to actually go from raw data sources into gridded emission files in a more traceable manner as part of SEMA and as part of MUSICA.
yeah, so that is another prong that we're following is having the model read the raw data files for emissions, directly doing the regridding as the model proceeds. But these are things in the work. I think we have finished the questions. So I want to reiterate that we will put a copy of the presentation up on the SEMA website. So here's a new question. SEMA can only handle NCAR models. Recommendation on configuring and using other models. So SEMA is the system for integrated modeling of the atmosphere. So it is, as Andrew showed at the beginning of the presentation, taking the modeling ecosystem at NCAR and giving it one infrastructure. I'm struggling a little bit to think, what else is being asked here. And so Andrew, maybe you can have a comment.
I think the answer is it can only handle NCAR models. It's envisioned as the infrastructure in which we're going to use to build modeling systems. Now, having said that, we're using an Earth system model, and the new OPSI tools will enable coupling other model components within that Earth system framework. So there are opportunities that Bill said. There's multiple ocean models that are being configured in that framework. So theoretically, you could actually configure another atmosphere model. You could use some of the things as part of SEMA to configure pieces of models. So we're going to be using common infrastructure for example, for physics parameterization. So it would be relatively straightforward to bring other submodels or physics parameterizations or aerosol models, chemistry models into that framework. So in that sense, the components of an atmosphere model you could bring into this framework if they come from other non-NCAR sources. And we have been discussing that with other people in the community, such as Geoschem, in making sure that that would be compatible with this framework. So in that sense, yes, we can actually handle other sorts of models through these common interfaces.
Yeah, and to follow along those lines, especially on the aerosol side of things, we are working with the community to find a way to have aerosol processes, physics and chemistry, interface with any atmosphere model. So not just CAM or MPAS, but other atmosphere models that are in the community.
And I should add that for the Geospace, what we're working on, coupling for either MAGE or just the Gamera for now, and in the future maybe SAMI3, the plasma sphere model. Those are external models. So we do have plan to work on those, and by partnering with our colleagues in the community.
Okay. So it looks like we are finished with questions. Gives everyone a chance to maybe ask one more, but we are getting close to the top of the hour. Again, we are recording the presentation, so that will be available if people want to see the recording. But also the slides will be available on the SEMA website. And as in terms of the polar comp set, the Geospace model output, and the MUSICA version 0 model output, you can also find those on the SEMA website under the SEMA version 1 applications. So, and then the last thing I think I want to remind everyone about is the Google form link to send us comments. So we'd love to hear your ideas and thoughts about SEMA. Do any of the other SEMA leads want to comment before we end the meeting?
I'll just say thank you all for coming. Thanks for your time. And our follow-up, we'll send an email with all these links so you can refer back to it later, and particularly with this comment form and things like that. So there is one last question. Are there options to anonymously submit concerns? Pseudo-anonymously, we didn't ask for anything on the Google form. If you want to do something anonymously on that Google form, you're welcome to actually provide a comment. I'm not 100% sure that Google will strip all your information, but we can keep that in confidence. And we can certainly keep it in confidence to ourselves, and we can get that communication. So please comment, and we'll be asking for that again, and we appreciate your time.
Yes, thank you everyone for joining us.